Hey guys, welcome to lecture number 4. At this point, well, I count this as lecture number 4 because the first lecture will be with the syllabus was lecture number 0. Some of you wondered what's going on in my background. You see here on my left is the University of Bucharest, where I graduated from. This is where I did my bachelor degree. So this is the capital of Romania. I found this very cool background, and I decided to have it on some lectures. Today we will talk about. You have seen last time in the previous lecture some things about limits of functions, and I showed you maybe 1 or 2 examples on how to compute limits, and we dealt with indeterminants such as 0 over 0, and I told you there are many others. There are 7 of them in total. And today I would like to show you more examples of limits and how to deal with them. So let's get started. All right. So today we will be talking about algebraic computations of limits. Like I said, you will see many examples today of how to compute limits, and you will see limits involving polynomial functions, limits involving rational functions. You'll also see limits involving trigonometric functions. And I think last time I told you about a certain limit involving a certain trigonometric function, involving sine of x. And I told you that sine of x for x small enough behaves like x. All right, and you also see some how to manipulate operations with limits. All right, let's get started. So common limit tricks. So just like I said, you have this thing over here, which says that the limit as x approaches 0 of sine of x over x is 1. So keep this in mind. This is very important. This will be essential for you. Unfortunately, we won't get to prove this until we talk about the L'Hopital rule, which is somewhat very late in chapter number 4. So once again, the limit as x approaches 0 of sine of x over x is 1. The way, if you want to write this in a different way, for example, if you don't like the symbol sign, you can also write this. So this will be equivalent. If you can also write sine of x, you won't put the equal sign, but you can put something like a squiggle like this. Sine of x is approximately x, and you put here as x goes to 0. Right? So we say that sine of x is approximately x for x is small enough. And I think the graph speaks volumes about this. If you look at the graph as x approaches 0, the limit will be the limit of sine of x over x will be 1. You see, this is the graph of sine of x over x. Okay, so keep this limit in mind. So this is a very important limit. Like I said, very, very important. So once again, sine of x over x as x approaches 0 will always be 1. Keep that in mind. And we will see today throughout the lecture, we will see a bunch of examples involving this limit. Okay. Now, let's see what are the common tricks, limit tricks. And I think I've mentioned this last time. Well, direct substitution, right? We said this last time. Basically, you plug the variable in. So that's what you do. You can do this for algebraic functions. You can such as polynomials, rational functions, etc. Just like we said. And this is very important. When you do this, for example, when you when you have rational functions, especially, make sure that the denominators are non-zero. This is important. So the denominators must be non-zero. This is, I would like to stress this, non-zero denominators, especially when you have irrational functions. So when you have rational functions such as, let's say f of x is p of x over q of x, right? This guy must be different than zero. So this is what we call rational functions. Right. So make sure you have this. Make sure you know that the denominators are non-zero. So basically, once you have this, you can just plug it in. Just we have seen this last time, right? All right. So that's the first thing you do. You do a direct substitution when you have a limit, and then after you do this, you see what result you get, and then based on your result, you see what to do next, right? Okay. And now I would like to, before we go, I would like to say a few things about the limit laws. What kind of limits do we have? And of course, if you look at the limit laws, for example, the first one, you have a constant there. So this guy here, so this guy here, so k is a constant. Right? So k is a constant. And of course, when you have the limit as x approaches some number of a constant, will always be the constant. For example, on the right-hand side, you will have an example. You see, the limit as x approaches 2 of 3. Well, if you look inside the limit, is only the constant 3. The constant 3 has nothing to do with what x is approaching to, right? So it will be 3, right? For example, what if I ask you, what is the limit as x approaches 100 of 99? Can you tell me? What is this? Louder so that I can hear.
99.
99, exactly. You see, the constant here inside has nothing to do with what x is approaching to, right? And pay attention here, the situation is different when you look at the second one, right? Just let's say this is the first one, this is the second one. The limit as x approaches a constant c of x. Now, just like we previously said, you plug it in and you have will be x, right? Will be c, sorry. So the limit as x approaches c of x will be c. We just plug in that constant. So in our case, if you look, the limit as x approaches 2 of x will be 2. For example, what if I say the same thing, the limit as x approaches 100 of x? It will be what? Can you tell me?
100.
100, exactly. See, there's a difference between these. In the first one, we had a constant, which was 99. See here? And here we have a function, which is x. So the quantity in the second limit depends on x. In the first one, we just had a constant, so there was no x, right? Okay, so I want you to distinguish between these first two. So the limit, you see, there is a difference. The limit as x approaches c of k is k, and the limit as x approaches c of x is c. So look at them very closely. Look at them here. See, there is a difference between them. All right, let's move to the third one. So the third one and the fourth one, as you can see, you see, we multiply a constant k by a function f. And when we take the limit as x approaches c, that constant k will just go outside the limit. So basically, you'll have that the limit as x approaches c of k times f of x will always be k times the limit of as x approaches c of f of x. So you're just going to take out the constant. And a good example, if you look on the right, you have the limit as x approaches 2 of 3x. Well, like I said, you take the 3 out, you're just going to take it out here. So it's going to be 3 times the lim as x approaches 2 of x. So let me put it like this, which is 3 times 2. And this goes back to here. See? That's how, this is how you operate using property number 3. For example, I can ask you something like this. What is the lim as x approaches 100 of, let's say, 99x? Can you tell me? What is this limit?
9,900.
So it's 99, let's say, times lim as x approaches 100 of x, which is 99 or times 100, whatever it is, right? 9,900, just like Cameron said. By the way, I would like to speak with other people as well, not just Cameron and another couple of you people. And so I would suggest you guys be active. Try to be as active as possible. Like I said, it will only play in your advantage. Okay. So that's the story with the third limit. So again, it's very important. So keep that in mind. Once you see a constant inside a limit, but make sure that constant is multiplied by something, by a function of x. Once you see that, then you don't have any problems. You can take that constant out and you can just you can play around with what's left in terms of x. So that's what you can do. All right, and now let's look at the fourth one, right? At the fourth limit, you see, I add these two. I have two functions, f and g. And I'm wondering, what is the limit as x approaches c of f of x plus g of x? Well, basically, in other words, the limit of the sum is the sum of the limits. That's what number 4 is all about. So, in other words, the limit as x approaches c of f of x plus g of x is nothing else than just limit as x approaches c of f of x plus limit as x approaches c of g of x, right? Keep this in mind. The limit of the sum is the sum of the limit. This is important. And in fact, you can combine 3 and 4, and you can just take the constants out as well. Maybe I'll point out here. And as an example, you see you have the limit as x approaches 2 of 3x plus 5. And this will, well, it's 11, but let's see how. Well, by the operation, this guy here, if you look at it, this is the lim as x approaches 2 of 3x plus the lim. So by applying operation 4, so let me put here 4. So this is the lim as x approaches 2 of 5, of the constant 5. Based on what we said, this is what? 3 times the lim as x approaches 2 of x plus 5. Now you plug it in, so you have it's 3 times 2 plus 5, which will give us 11. It's exactly 11 what we wanted, right? So that's these are the details. And now let me combine 3 and 4, and let me write it in the following way. So combining 3 and 4, we will get that the lim as x approaches c of, and I'm going to say here a constant, let's say alpha f of x plus beta g of x. This is nothing else than just alpha times lim as x approaches c of f of x plus beta lim as x approaches c of g of x. You see, by this holds true by combining 3 and 4. Right. Because in number 4, you have those constants are 1, right? It's 1f of x plus 1 times g of x. But anyway, you can have this more general limit by just combining 3 and 4. All right, let's move further. Let me talk more about limit laws, because now we want to see what happens with the product, with the quotient as well, with the power, and as you would expect, the same thing holds true. So this would be number 5. And let's read the first one. In other words, the first one says nothing else than the limit of the product is the product of the limits. So we have that the lim as x approaches c of f of x times g of x is the limit as x approaches c of f of x times, right, because we have a product now, times the limit as x approaches c of g of x. Right? So the limit of the product is the product of the limit, once again. All right. As an example, we have that the lim as x approaches 2 of, and I take those two functions, let's say this guy here, so this guy here is f of x, and this guy here is g of x. And as you can see, this will be nothing else than, so this guy will be, so this guy here is nothing else than the lim as x approaches 2 of 3x plus 5, right, times the lim as x approaches 2 of x plus 1. But each limit, once you plug it in, so it will be 3 times 2 plus 5, 3 times 2, which is 11, right, 11 times 3, which is 33, and there you go. Right? This is just basic operations with limits once you apply the product formula, right? With the limits. I want to call it product formula because we will have a name for that when we study derivatives. But anyway, that's the rule. So once again, the limit of the product is the product of the limits. So keep that in mind. Okay. Now, let's see the sixth one. The same thing will happen for the quotient. So the limit of the quotient is the quotient of the limits. So the lim as x approaches c of f of x over g of x is the limit as x approaches c of f of x over the limit as x approaches c of g of x. Provided that, so I want you to pay attention because this is important. We said this at the beginning. Provided that we have this here. So the lim of the denominator is not 0. Keep that in mind, right? So this is quite expected. It's common sense at the end of the day. All right. And now let's see. Let's see an example. And if you look at this example, as the limit as x approaches 2 of 3x plus 5 over x plus 1. Well, this is nothing else than just the limit. The limit of the quotient is the quotient of the limit. So it will be, okay, let me put the fraction first. So this is lim as x approaches 2 here of 3x plus 5 over lim as x approaches 2 of x plus 1. Well, the first one, as we have previously seen, is 11, and the second one is 3. So it's 11 over 3, right? Okay. And let's see, the seventh limit is when we have the limit of a function f of x raised to some rational power. In other words, we have that the lim as x approaches c of f of x, everything raised to the power a over b, that rational number, right, is the limit as x approaches c of f of x, right, everything raised to the power a over b, right? And as an example, just look at this guy here. Lim as x approaches 2, actually the details are written in the slides, so there's no need for me to write anything. So if you have, as an example, if you want to compute the limit as x approaches 2 of the square root of 3x squared plus 4, you can just plug in x equals 2. And once you do this, you see, but first you need to, well, you don't need to, but you can do it so that you can emphasize the rational power. You see, the square root is nothing else. Well, let me write it here. The square root of a is nothing else than a to the power 1/2. So let me remind you this from college algebra, and you will have that the limit as x approaches 2 of the square root of 3x squared plus 4 is nothing else than the limit as x approaches 2 of 3x squared plus 4, everything raised to the power 1/2, and then you can just plug it in, x equals 2, and then you just do the computations. And this will give you square root of 16, which is nothing else than 4, or 16 to the power, okay, let me write it here, 16 to the power 1/2, which is 4, and that's the result. All right, I think you got the main idea of what happens, right, with this limit. So these are the laws, keep these in mind. See, the 7 laws. Once again, you have a constant, no problem. The limit will be that constant. You have a constant times the function, again, no problem. You take the constant out. You also you have the limit of you add 2 functions and you want to take the limit, no problem. The sum of the limit of the sum is the sum of the limits. The same thing goes for the product. The same thing goes for the quotient. The same and for the same thing goes for the power limit, right? You have a function, you raise the limit to that power, no problem. The same thing will happen, right? All right. So these are the limit laws. This will be very important because we will operate with these guys in examples that will follow. And now let's see a first example. I want you to look very closely at it. Very simple example. And I would like you to tell me, what would you do to this? Think about it for a minute, and I would like to hear some other people as well, other than Cameron. I see someone here. Abdul says, well, you replaced it with 2, right? What did we say at the beginning? We said that we would like to plug it in. So we plug 2 in. plug in x equals, okay, let me write that. That's what we do, right? We said this at the beginning. So once we do this, let's see, what do we have? Well, when we do this, we have this. Basically, you just plug in x equals 2, so you'll get that the limit will be nothing else than just the limit as x approaches 2 of 2x to the 5th minus 9x cubed plus 3x squared minus 11 will be nothing else than just 2 times 2 to the 5th minus 9 times 2 to the 3rd plus 3 times 2 squared minus 11, which is -7. And well, this is just a computation, right? So that's the secret to this problem. So this was a fairly easy one. Now let's see another one. Think about this. What would you do here? Well, as Kyle says, well, we can plug in x equals 1, and let's see what happens. First, exactly, yes. Yes, we first plug in 1. So let's see what happens. So when we plug in x equals 1, you will get, you see, once we do this, you get exactly a finite number, which is great. So you will get that when you plug in x equals 1, you will get that the limit as x approaches 1 of 3x squared plus 7x minus 2 over 5x plus 2 is nothing else than just 8 over 7. Just plug it in and you do the operation. So, okay, that's again a fairly easy one. And we're lucky in this situation. But now let's see some other common tricks. Maybe we won't get that lucky. And we said the second one was just to plug it in, but what if it doesn't work? As we have seen in previous lectures. I showed you indeterminate, which was 0 or 0, right? We talked about this. And well, another trick is to factor. So we will be talking about factoring. Well, basically when evaluating limits, simplify the rational expression as much as possible to avoid dividing by 0. This is very, very important. So try to simplify as much as possible, because you would like to avoid by dividing by 0, right? So that's the trick. And you make use of this factoring trick once the previous step, like this one here, by plug it in, doesn't work, right? As we have seen in these examples, this one and this one. So, right, keep this in mind. All right. Once again, when you evaluate limits, simplify the rational expression as much as possible. In fact, your main goal is to avoid dividing by 0. That's what you want to do. You want to avoid dividing by 0. All right, and now let's see an example. Sorry about that. And let's see how. Let's see this one. So how would you deal with this one here?
Factor.
So like Exxon, how do you pronounce your name? Exxon? Exxon. Anyway, yeah, exactly. But first, before we even factor, what do we need to do? We need to plug it in, right? So once we plug it in, if you look at it, so first let's plug in. And if we do this, what do we get? So first plug in. Plug in x equals 3. That's what we do, right? So let's see, what do we get? So we get that this is 3 squared minus 3 minus 6, everything over 3 minus 3. So what do we get? On top, exactly, 0 over 0. Exactly. Yeah, like Bryce and Frank said, yes, 0 over 0. So unfortunately, this is an indeterminate, so it's undefined. So we need to do something. Well, what did we say previously? We want to say simplify the rational expression as much as possible to avoid dividing by 0. So in other words, maybe there is a way for us to express the top in terms of the bottom. Maybe we can factor the top in terms of the bottom, and that's exactly what we're going to do. And indeed, we can factor x squared minus x minus 6 as x minus 3 times x plus 2. We can do this, and as you can, and we're lucky now because we have that the top is can be expressed in terms of the bottom. And we just have to cancel x minus 3 here, right? Boom, boom. And that's it. You'll get the limit as x approaches 3 of x plus 2. And now you plug it in and it will be 5. That's exactly what we can do, right? So that was the trick to this problem. All right, let's see another example. Well, I'm going to spoil it here a bit. Look at this. And I want you to look at this very carefully. So we would like to evaluate the limit as x approaches 2 of x cubed minus 8 over x to the 4th minus 16. But first, we need to plug it in. So if we plug it in, so we have 2, if we plug in x equals 2, you have 2 cubed minus 8, right, over 2 to the 4th minus 16. And this would give us, again, 0 over 0. This is undefined. So now maybe we should use some similar tricks of factoring, but as you can see now, the top, both the top and the bottom can be factored, and can be factored in a very particular way. You see, on the top we have the sum of 2 cubes, because 8 can be written as 2 to the 3rd, right? And I can use this amazing formula here. Look at it. Let me remind you from college algebra. So I can use this here on the top, but also here, this one, I can use this one here. So I can to the bottom. I have this other amazing formula. So make sure you remember these formulas. I think you have studied them in college algebra, in pre-calc for sure. And once we know this, well, the situation will become pretty clear. Look, just like I said, we use the difference of cubes for the bottom and difference of squares for the top. The difference of cubes for the top and difference of squares for the bottom, sorry. And once we do this, we can factor the top as x minus 2, as you can see. We can factor as x minus 2 times x squared plus 2x plus 4. And the bottom can be factored as x minus 2 times x plus 2. But here, maybe I should say one thing, because we applied the difference of squares twice, and maybe I should make myself clear. So let me write it here, x to the 4th minus 16. So this guy is x squared squared minus 4 squared. So this is x minus 4 times sorry, x squared minus 4 times x squared plus 4. But I can also write x squared minus 4. I can use the difference of squares again. So this will be x minus 2 times x plus 2 times x squared plus 4. And once we do this, look what happens here. This guy will go with this guy, and I will have this guy here. So have the limit as x approaches the 2 of x squared plus 2x plus 4, everything over x plus 2 times x squared plus 4. And now, again, we can plug it in. So once we plug it in, and let's see what happens. I'm going to write here. So it's 2 squared plus 2 times 2 plus 4, everything over 2 plus 2 times 2 squared plus 4. And so guess what? You'll get exactly this guy here, 3 over 8, right? Anyway, I'll leave the computations to you to figure them out. But that's the, you see, the trick was to use these two identities. It was a little bit tricky, but I'm sure you got it. Do you have any questions regarding this example? Is it clear for everybody? Okay. There are no questions. I suspect that this is clear. All right, let's see some other common tricks. And the fourth one is to rationalize. And you will see exactly how to come up with this when we deal especially with radicals. So, some limits cannot be evaluated by direct substitution and no factors immediately cancel. That's the problem. Well, we will try to rationalize this. And what do we mean by this? So this is what you have to keep in mind. So we would like to try this, what we call rationalization. And with this technique, we use properties of the conjugate pairs to make the numerator or the denominator of an expression rational. So that's the goal of rationalization. By using the so-called conjugation process, and like I said, this will be important when we deal with radicals, especially, you will see that. So one of them, it doesn't matter which one, the top or the bottom, you will have to make that a rational number. So that's the trick of rationalization. All right, well, I won't call it a trick. It's a procedure, in fact, you can recognize it. All right, so let's see an example. Just like I said, you have an example like this. So now we would like to evaluate the limit as x approaches 0 of the square root of x squared plus 9 minus 3, everything over x squared. Look at this. Try to think about it for a couple of minutes and we'll explain immediately. So if you plug in x equals 0, what do you get? Can you tell me? So what do you get?
0 over 0.
Again, it's 0 over 0. So when you plug it in, so you'll have 9 square root of 9 minus 3 over 0, which is again 3 minus 3 over 0, which is 0 over 0. Again, this is undefined. Oh my God. Again, we don't like that. So what should we do? You have the radical, and let me go back. You see, we like to multiply by the conjugate. So we multiply by the conjugate. This is n here, by the conjugate. So what is that thing? So this is how we rationalize. And I'm going to write it here so that you can see. In fact, no, let me. So I'm going to write here the expression again. So it's the square root of x squared plus 9 minus 3, everything over x squared. You see, Can you tell me where do you have radicals here? On the top, right? So maybe we can multiply by the conjugate, which is the square root of x squared plus 9 plus 3, right? So once you do this by multiplying by the conjugate, basically you multiply the top and the bottom by this. Ouch. Sorry about that. So we will have that this is the square root. Okay, let me write it like this so that you can see. So here I'll have, so this would be the square root of x squared plus 9 plus 3 times the square root of x squared plus 9 minus 3, right? Everything over, okay. So everything over x squared, and here times this guy, the square root plus of x squared plus 9 plus 3. You see, I multiplied the bottom and the top by this. Now, what can you tell me about what happens on the top? Again, I will use that trick over there. You see this one here? Oh no, yes, exactly. See the difference of the squares? This time I'll have with the square root, and this would be what? Well, once we do this, let me tell you exactly what happens. Look. You see, that's exactly what we're doing. So this is the conjugate. Well, it's written, so this is the conjugate here, just like I explained. In other words, the conjugate of this, well, okay, let me write it clearly. In fact, I will, so by the conjugate, in fact, I can write here, the conjugate of the square root of x squared plus 9 minus 3, which is the square root of x squared plus 9 plus 3. That's the conjugate of this guy. Keep that in mind, right? All right, once we do this, guess what? We're going to obtain this rational function here, rational expression here, right? As this would be nothing else than the limit as x approaches 0 of x squared plus 9 minus 3 squared. And guess what? They will just cancel. And this would be, if we go further, as you can see, these two will cancel, right? So these two will just go away here, and you'll get this guy here. And now you can plug it in, and this will give us 1/6. Right? Is it clear for everybody?
Wait, could you please go back up one slide?
You see, when you multiply these two here, maybe I should explain a bit here. So the square root of x squared plus 9 minus 3 times the conjugate here, the square root of x squared plus 9 plus 3. This is the difference of two terms. You see, this is, let's call this an a, let's call this a b. This is a minus b, and this is nothing else than a plus b. And we know by the formula this is a squared minus b squared. So this guy will give us nothing else than just x squared plus 9 minus 3 squared, which at the end will be x squared. So that's what we need to know here. Right? So once we have this, and now everything just goes smoothly. right? Because you'll have, you see, once I multiply by the conjugate, both on the top and bottom, we will get this. And then at the end, you will have that this is nothing else than just the limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3, which is 1 over 6. I hope this makes sense for everybody. All right, let's move to another example of this very similar example. And now, since we have in mind what happened, can you tell me how should we proceed in this case? So what would you do? The first thing, very first thing that you would do is what? Plug it in, correct. When you plug it in, this would be what? This would be the square root of 2 plus 2 minus 2, everything over x minus 2. Again, we'll get 0 over 0. Oh, I don't like that. It's undefined. No problem. Okay, I get 0 over 0. What should I do to this fraction? Multiply by the conjugate. Exactly. We need to find the conjugate. So we multiply by the conjugate. I'm going to multiply here. And what is the conjugate? Will be what? Will be the square root of x plus 2 plus 2. So this is the conjugate. So multiply by the conjugate. That's what we need to do. All right, let's do this. And look what happens. When you multiply by the conjugate, which is the square root of x plus 2 plus 2, we will get this. And once again, when you multiply here, this guy, when you multiply these two here, the top, again, you will use the formula, you will get exactly this one here. It corresponds to this one. And then the bottom will stay the same, right? Okay. Now the top, as you can see, we have at the end x minus 2. So I'll write it. So this is x minus 2 over x minus 2 times the square root of x plus 2 plus 2, which is great. But now, guess what? These two will just cancel. And then you'll end up with the limit as x approaches 2 of 1 over the square root of x plus 2 plus 2. And now you can safely plug it in and you'll get exactly this guy here. It's 1/4. Right? So it was a very similar prototype, this example with the previous one that we just discussed. So once again, when you see a rational function and both of them are polynomials, basically they don't have any square roots or nothing, you can think of a factoring trick. But when you see a rational function, but the top or the bottom is a radical, you think of rationalize, or basically multiplying by the conjugate trick. So keep this in mind, right?
Could you please explain how you're getting from x plus 2 minus 2 squared to the just x minus 2?
Here, you see, this guy here is x plus 2 minus 4, which is x minus 2. That's what you asked?
Yeah, thank you.
Right? And then you get x minus 2 over x minus 2, and then they will just cancel. All right. Let's see some other tricks. What if we deal with limits which will involve trigonometric functions? What if this is the case? What will we do? You see, just like I said at the beginning, the special trigonometric limits. So the first one I have already said it at least twice by now. So the limit as x approaches 0 of sine of x over x is 1, as we can see also by just looking at the graph. Somebody says here, I hate trigonometric functions. Well, you'll be surprised that they're much more present in our lifetime. Even, for example, when we transmit now, our live transmissions through Zoom, at the base, it will involve trigonometric functions. The signal that I'm talking right now, and I'm sending you a signal so that you can hear me, right? Through the laptop and the iPad. And you'll see that the signal, it will involve the so-called wavelets, and this will be nothing else than basically at the end of the days, it will involve some polynomials involving sine and cosine. So I hate to disappoint you, but these trigonometric functions are very, very important in our lifetime, especially now you guys are engineers. So at some point in your life, you will do Fourier series. You cannot live in engineering without Fourier series. Guess what? Fourier series that you will learn in all those classes that you will take. First of all, you'll learn about them in differential equations class, and then you'll encounter them later on in your physics class or maybe even engineering class, not maybe, definitely in other engineering classes as well, and you'll deal with them plenty of time. So I would suggest you take them very seriously, and this starts with these two trigonometric functions, these two limits, which would be important. So like I said, the first one I have already emphasized on the first one many times, but the second one is this here. Exactly. So now the second one is the limit as x approaches 0 of 1 minus cosine of x, everything over x will be 0. But you see, if you plug it in, x equals 0, you have 1 minus cosine of 0, which is 1. So you have 1 minus 1, everything over 0. Again, this will be 0 over 0. So it will be kind of indeterminate. And the same goes for the first one, right? When you plug it in, right, for this one here, when you plug it in, x equals 0, you'll get that this sine of 0 over 0, which sine of 0 is 0, so get again 0 over 0. So both of them are undefinite if you plug it in. So that's why these two limits, this hold true. Anyway, I'm not going to go into the proof of these two now. Like I said, there are some elementary proofs of this, but I don't want to waste my time with it. They're pretty tricky, and we will also prove them once we learn about differential derivatives and L'Hopital rule. But so far, this is what you need to know, these two limits. And we would like to use them in some, when we deal with trigonometric limits. And now an example is this one. So how would you approach this guy here? So the limit as x approaches 0 of sine of 3x over x. So first, what would you do? Again, you plug in, right? So when you plug in, what do you get? When you plug in x equals 0, what do you get? Again, 0 over 0, correct. So you have 0 over 0, which is undefined. So what would you use here? You see, you have something involving sine. So you would be tempted to go back to this guy here, right? You see this one here. So maybe we should use this one. And indeed, we can do that. Yeah, but the only difference is that we have a 3 there. No problem. I can multiply and divide by 3, as you can see now. And now this guy here, see this guy here can be expressed as, can be expressed as the limit as x approaches u, let's say, as u approaches 0, sorry, of sine of u over u, right, which is 1. Because in our case, u will be 3x. And as x approaches 0, 3x will also approach 0. So this will approach 1, so this is 1. Okay, maybe I should write a little bit more details here because it's not quite explained the way. So this will be 3, so the constant 3 will go outside the limit, right? All right, so this would be 3 times the limit as x approaches 0 of sine of 3x over 3x. But this guy here, this is 1. So this will be 3 times 1, which is 3. Exactly what we got, right? All right. Let's see another one. What do you think? A very similar one. What do you think about this one? So we would like to evaluate the limit as x approaches 0 of sine of 4x over 5x. What would you do here? First, again, you plug it in. Always you do that. When you plug it in again, you'll get 0 over 0, which is undefined. All right, you get 0 over 0. But now again, we would like to use, so we would like to use what? To use the fact that the limit as u approaches 0 of sine of u over u again is 1, right? We want to use this guy. So maybe we should divide by 4 and multiply by 4, and that's what we're going to do, as you can see here. So the same trick goes. And now, once we do this, it's very similar. So you see this guy here, we're going to take 4 over 5 outside the limit. So this would be 4 over 5 times the limit as x approaches 0 of sine of 4x over 4x. And as x approaches 0, 4x will approach 0. So you can apply this here, where u equals 4x. Right, as x approaches 0, u will approach 0. So this will be, this is the 1. And guess what? It will be 4 over 5 times 1, which is 4 over 5. Right, so it's very similar. Okay, here we go. What if we have tangent? You see, maybe I didn't mention here, but the same thing goes for tangent. Let me write this. The limit as x approaches 0 of tangent of x over x will be 1. So keep this in mind. So we have that the tangent of x is it's approximately x as x is small enough. So we would like to use this, and we will use this on both, on the top and the bottom. But first, when you plug it in, you see, you'll get tangent of 0, which is 0, over tangent of 0 over 0. So again, it's 0 over 0 is undefined. You see, so the plug it in method doesn't work. So that's why we need to do something. Well, you can express it. You can do it like this. So let me just, it's a little bit more complicated, but basically it just uses the fact that tangent of x over x equals 1. So let me explain this method first. So you see, we can write tangent of sine over cosine. Well, in this case, so far yeah, I see a question here. Will everything start out as 0 over 0? Well, no, not everything. Oh, so far you have seen only examples of 0 over 0. You also see other examples of infinity times 0, or infinity over infinity, or other 1 to the power infinity. Those are undefined as well, but there will be other methods to deal with those, and we'll see that later on. So once again, here you will see I can write the tangent of sine over cosine. I'll do that. And then once I do this, and I apply the limit of the product is the product of the limit. And then, well, I see this thing here. So I'm dealing with each limit here. Because cosine, when I plug in cosine of 0, so this guy is, okay, so as x approaches 0, cosine of 2x is 1, approaches 1, and cosine of 3x will approach 1. Right, so they're both 1. So at the end of the day, we'll just rely on the fact that, so again, this will be 1 here. So it's 1 over 1, which is 1. You see it here. So the only thing we need to compute is this limit here, that is the limit as x approaches 0 of sine of 3x over sine of 2x. Again, the same trick goes, because I would like to use the fact that sine of in terms of, you don't need any identity in terms of sine and cosine. No. You plug it in. So this guy here is 1, but just plug it in. So the only thing you need to deal with is this one here. And for this one, like we said, I'm going to use the lim as u approaches 0 of sine of u over u, which will be 1. So I'm doing the same thing here. I'm multiplying and dividing by 3. And again, now and the same thing goes for sine of 2x. I'm doing the same thing. But the only thing is that you're going to get that on the bottom. So as you can see here, highlighted in red. And now guess what? This guy, once we do this guy here, so this guy here is nothing else than 1 because of this. And this guy here, let me write it again. So this is, if you look at it, is 1 over the lim as x approaches 0 of sine of 2x over 2x, right? And again, this will be 1 over 1, right? Which is 1. So it's 3 halves times 1, which is 3 halves. And you see it here, right? Okay. Now, another common trick, and well, unfortunately, I'm going to go a bit over time, is the squeeze theorem. This is very important. The squeeze theorem. So if I have two functions, let's say f between between g and h. So I have this inequality, g of x is less or equal than f of x, less or equal than h of x, and the limit as x approaches c of g of x is the same as the limit as x approaches c of h of x is L, then there is no escape for f. The same thing will happen for f as well. So the lim as x approaches c of f of x will be L. So in other words, let me draw a picture so things are clearer. We have g of x less than f of x less than h of x. This goes to L. This guy goes to L as x approaches c, both of them. Well, guess what? The same thing happens for this one. We'll go to L as x approaches c. Well, in Romania, we used to call it, in a popular language, we used to call it the criteria for the two policemen. So if the two policemen grab you and they go to the station, there is no way you can escape. You'll get to the station as well because you are between them, right? So the same thing goes here. So this is the squeeze theorem. And now let's see an example of the squeeze theorem. And the example is this limit as x approaches, and I said a few things about this kind of limit, maybe not with x squared, but with x definitely. So we would like to evaluate this. Guess what? As x approaches 0, sine of x will have some problems. So this guy has problems. The limit does not exist. So this guy has problems. Right? But maybe we can squeeze this, but it has an advantage. It has problems at infinity. But at least it's bounded. But at least is bounded. The guy is bounded, which is great. So I can get rid of it. Since you have problems, when you have a problem with somebody, when you want to get rid of that somebody or whatever, right? Something. So guess what happened? Sine of x is, since we know it's bounded between -1 and 1, then so sine of 1 over x is between -1 and 1. And guess what? I can squeeze these two. And once I do this, good things happen. So the limit, both limits, you see, these are, let me draw a picture again. See, negative x is less or equal than x squared sine of 1 over x less than x squared. These two guys will go to 0 as x approaches 0. Well, the same thing happens for this guy as well. So that's the picture you have to keep in mind. So the limit is 0, right? So the only thing you need to do is just to get rid of sine of 1 over x. Okay, great. Let's see another example. The same things go for this one. You see, again, I have cosine. As x approaches 3, cosine, again, is a periodic function. It will have problems at the infinity. So cosine of 1 over x minus 2 will have some problems. So I'm trying to get rid of it. Again, this guy has problems, but is bounded. And you can look at this by just look. You can look at the graph and you'll see it. So the same thing goes here, right? You see, cosine, again, this guy is between -1 and 1. So between -1 and 1. So, and I can neglect this, no problem. I'll do the same thing. And again, by the squeeze theorem, since both of these two guys here will go to 0 as x approaches 3, there is no escape for that guy over there involving cosine. So again, it will go to 0, right? And now, well, what do I mean? Well, when I say this guy has a problem, he also, yeah, at first it has a problem on the denominator. First of all, it has 0, but let's just leave that aside. It's cosine of 1 over 0, which can be plus minus infinity. Cosine at plus minus infinity does not exist. So keep this in mind. So by just, if you want to apply the product rule, you'll take, okay, no problem, I'll apply 0 times something that doesn't exist. I don't even know what the hell is going on. Even if that something will be infinity, I don't know what's going on. So that's what, this is what I say, cosine and sine at infinity at 1 over 0, which is, like I said, it can be plus minus infinity, has problems. But when somebody has problems, but at least it's bounded, you can get rid of it. And this happens with the sine and cosine. I hope, Abdul, this answers your question. All right. And now let me draw, I'm going to go a bit over time, and I will apologize for that. Let me show you an example of how to compute this limit. Look at this. I have this, given this function, x squared minus 5, find this limit. We will call this guy here And this will be important when we talk about this is what we call difference quotient. And I would like you to keep this in mind because this will be intimately related to the derivative of the function. In fact, this limit will be nothing else than just the derivative of the function, surprisingly. So we would like to evaluate this limit as h approaches 0 of f of x plus h minus f of x. So this is, in fact, let me be specific. This is the difference quotient. Only this guy here, not just the. So now the limit of the difference quotient as h approaches 0 will be nothing else than just the derivative. But anyway, I'm not going to go into details about this yet. So now we just have to plug it in. You see, I'm evaluating this limit. So since f of x is x squared minus 5, then you can plug it in and you'll get that f of x plus h will be x plus h, everything squared minus 5. And minus f of x, which is x squared minus 5, everything over h. And now you do the algebra. And once you do the algebra, you see here you have a negative sign that changes. So this guy here will be negative x squared plus 5. You see the 5 will cancel. The same thing goes for the x squared. And then you'll get that this will be nothing else than just 2xh plus h over h. And now we can factor an h. Right? You see, we have this. I can factor an h here on the top. See, it's pretty clear. And then I will just cancel h here. And once I do this, I will obtain a limit as h approaches 0 of 2x plus h. And now I can plug in h0, and I'll get the final result, which is 2h. So the moral of the story of this example, well, I went a little bit faster. The moral of the story of this example is that the derivative of x squared plus x squared minus 5 is nothing else than 2x. And that's the procedure you go through. Anyway, and the same thing will go for this one. And I'll leave this to you as a homework to look at it. So homework. So the same thing goes for this one. Right? Anyway, you look it up and try to do it by yourself. All right, guys, I think I'm gonna stop here for today. I'll see you on Monday. And we'll start something new on Monday. We'll talk also about continuity. Okay, I'll see you. Take care, bye-bye.